So let's just like present my entire screen. Okay, can you oh yeah, okay, I think it should be fine now. Let me just look at it. You are given two strings s and t considering of lowercase Latin letters. Length of t is 2. In one move, can choose any character of s and replace with any lowercase Latin letter. No more than k replacement maximizes the number of occurrence in t in s as subsequence. Okay. So the first thing that like I will think of when reading the problem, right, is that I will first think of like what if k equals infinity. Okay. So if k is infinity, then we will have, then the best thing for us to do is that the first ends, like let's say we have a string of length 6, right? Then we also let t equals ab. So we will fit like the first half of the string with a and the second half with b. Then like the number of like substrings you can get is like 3 times 3. Okay. Yeah. But unfortunately this is not the case. So, and you can try to like modify this a bit, but I don't think it'll lead you anywhere. So yeah, well, the first thing we can notice, so yeah, let's try to like think of like some simpler observations. So observation 1, when you replace a letter, you should replace with either t0 or t1. I mean, this is clear why you need to do this, right? Because if you don't do this, you're kind of just like, if you replace it with some other letter than t0 or t1, you're kind of just wasting your moves, because it doesn't it doesn't help you to form any other substrings. Okay, so let's think of something slightly unrelated. Let's think about like how can we count number of substrings of length 2. So there's an O(n) squared way, right? I mean, the O(n) squared way will be look something like this, like for I in range, and then we have for j in range I plus 1 to n, if si equals to t0 and sj equals t1, then we add 1 to answer. This will be n squared way, but isn't there a faster way? Is that a faster way? Yeah, this is being recorded. What do you mean subsequences? So this is the O(n) squared way, right? So is that a faster way to count the number of sequences of length 2? I mean, the count, subsequences using prefix and suffix arrays. Yeah, so how do you use prefix and suffix arrays here? So yeah, let's like iterate I in range, let's do like j in range n, right? Then answer, then if sj is equal to t1, answer plus equals the number of si equals t0 such that I is small j. Okay, makes sense so far, right? Yeah, like this code should be equivalent to this code. Then for this thing, right, how to find this one, use prefix sums. Okay. Yep. So now let's think about it. What do we actually need for DP? Like, let's say we want to have a dynamic programming solution, right? So DP, we have some state equals some answer, right? What do you need to store in state? So we need to store like in this process. I mean, that's like the most common thing we store in a DP. Then what else we need to store? I mean, we also want to store like number of replacements used. Then what else do we need to store to like calculate answer? If you look at here, right? So this is look at here. Our answer only depends on number of SIs that equals T0 such that I minus J. So why not we just put this in our DP state? So this will be J. Okay, following so far? So do you see how this DP allows us to compute our answer? And this DP state, right? What's the number of states of this DP? The number of states is n, because there's n possible J, and then we have K. That's the number of replacement used. And this number of SI is also K. It's also n. And this DP can calculate the answer. Do you follow? I mean, I can do a coding. I can do a coding for you. So let's read all the input first. So our DP consists of these states. Okay, so let's just build our memo table. I prefer coding DP from top down, so yeah, I'm going to code it top down. So dpj replacements and then like number of this. So we want to find the answer of the last element. Then we use k replacements and well, we need to iterate on another thing. So the answer is a maximum of like. So the position for the correct answer will be the last position of S, and we use k replacements, and the number can be doesn't need to be like fixed, so we need to iterate on X. So let's write the DP. So if we calculate the DP before, then we can just return it. Otherwise, let's calculate our DP. Let's handle our base cases first. So if j equals to -1, then we must have that the number of replacements used is 0, and the number like this value should also be 0. So then return 0, that's good. Else we need to return -infinity. So I'll use -1e8 then. You cannot view the screen. What do you mean? I'm showing my IDE right now. You can see my IDE, right? Yeah. So handle the base case, then we handle the general case. So the first case is that if Si equals A, so change Sj into A. So num2 will be a new cause. So rep2 is like the new number of replacements used, because we need to minus off if this thing isn't A. Then we also need to like update a new num2, so num2 is num minus 1. So we get this dp state. Oh yeah, before I do that, let's let's just like write some code to like make sure that we handle the cases where we get invalid values. So this should handle all invalid values already. Okay. Then second case. Change it into B. So num2 is still same, and rep2 we need to change it to this. Forgot to do a close bracket here. Then now don't change Sj. So pretend it isn't T0 or T1. Okay, let's put T1. Yeah, it isn't always A and B, but so let's change it. So here the number of replacements and the third dp value is the same. So just this. Now we just return our dp. So let's test if this works. So this fails samples. Okay, let's debug that. So this seems to fail samples when we have T1, T0 is T1. So let me just try on this. Yeah, it seems to work. Did I read the statement wrongly? Number of occurrences in T as subsequence. And you can obtain the string. Okay. So we need to have an okay, so here I'm considering I need to have another case where T0 equals T1. Then here I'll plus num2. So this should work out. Yeah, this is badly written code, but I think it's probably should do its job. Let's see, does it pass the... Okay, wrong answer on test 6. I'm just gonna look at it. We got 0. Okay, let's try This is... Okay, so I made a mistake in my DB state, but... So there isn't like any reason to... Okay, this is correct, right? This is correct. But, you see, the answer became worse if... The answer became worse when like I changed k to a higher value. So, actually there's a mistake here. So k does not need to be fixed also. We can also check everything below k. So x can take any value from 0 to k plus 1. Let's submit this now. Let's try submit this. Yeah, it seems to pass. If everyone understands, you can like send other problems in. If you want, you can send other problems that I can go through. What's this problem? Okay. Is this like the last round of the div 2? Let me check. Second last. So let's say you have, so I'm going to consider this tree. So you have some tree like this, then you have some. So when do you cut the tree such that the x are in the same component? Well, we can only split the x, right, when we cut along the line that joins the x. So only when we cut through the red line, then we split the x. If not, anywhere else we cut, it's completely fine. Now what if we have 3 vertices instead? So if we cut the tree anywhere here, right, then the mat, like the MAD, like that goes inwards towards the tree. Like that's it's just here, the MAD is all gonna be, it's like they'll all have x in like one component. Okay. Take the maximum of 2 values. Okay. Take the maximum of 2 values. So yeah. Then how about if you have 3 x's here? Let's imagine. Let's imagine a few cases. So far no questions. So if we cut this here, we can have like 3 x's on one side. You cut this here, gonna have like 2 x's on like this side. If we cut over here, gonna have 2 x's on this side. So actually, right, no matter how you cut the tree, there will be at least 2 x's on one side, because what's all the possible ways they can split the x? Like you can split left side, one side has 0, one side has 3, one side have 1, the other side has 2. Like, you notice that in every way of splitting, the maximum will always be at least 2. So we only need to care. And then what happens? Okay, if there's only one single x on the tree, right, then the MAD will never be x. So we only need to care about what happens when there are exactly 2x on the tree. So when there's exactly 3x on the tree, right, the MADs are at least x already. So this will be, so everyone follow so far? So we're gonna try to work like this. So let's say, let's take the sample. We will work in the order of like the so first let's process tree. There's only one vertex tree that in this tree, so nothing's gonna happen. Now let's do 2. So 2 we have here and here. So everywhere there is this path from, there is exactly 2 2s on the tree, right? So we will draw this path. And everywhere it's not on the path, the MAD is 2. Okay. How about the green color one? The green color we have this one and this one. So there's this path, then everywhere there's not on the path that we haven't written a 2, right, we'll write a 1. So this is the respective MAD of the edges. Then for this H12, right, where we've written nothing, the MAD will be 0. Okay. Now this process is n squared complexity. So now we want to ask, can we make it faster? And the thing is that we can actually make it faster. How do we make it faster? Well, the first thing you realize is that after the first step, right, the tree becomes a line already. The tree becomes a line, because we remove all these edges. The tree must become a line. Then when the tree becomes a line, right, it's very easy to handle. Because the part that is labeled 0, that is not labeled yet, they form a kinetic component. So in effect, right, what you can do with this line is like you can only like remove the like one side, or you can like remove another one side. So let's just code that. So what do you need to output? You need to output the maximum of the after removing the given edge from the tree. Okay. Let's also have an array for answers. So we'll read in our input first. Now we will do now we will sort like we also read in the array ARR. Like this is the numbers of the vertices that we'll read in the array R. So to make it easier to process this, let's just sort this array by like the weight of the vertices. Let's check this is working. Yeah, so this seems to work. So 3 is the largest index, followed by 1 and 4 with value 2, and 2, 5 with value 1. So let's do this. So let's do like some sort of 2 pointers to figure out like which ranges have like the same have the same value. So initially r equals L, then while r equals to we change this, we'll add r. And finally, to continue the for loop, L will be equals to R plus 1. So let's just check if this works. Oh wait, mistake. We should have put index because we didn't sort it initially. So yeah, all following so far. Now, if L equals R, nothing happens. If L plus 1 equals R, then this is like the special case where we have to like, you know, ignore like everything on the path from the two same values and write the answer and everything else. Well, in the other case, then it's very simple. We just it's just the answer is just the maximum of this. And here we can just break already, because here we can just break. So this is like this is the only hard part. Okay. Now, one of the more like easiest to code ways I can like think of how to handle this is like to use DSU. So let me just quickly go with DSU. I don't usually use templates for DSU because I can code them quite quickly, so I just code them. I'll just code one right now. And yeah, this is just be your DSU. Now, another annoying part is that we need to like actually find this original chain first. So we still need to. So we'll need to do a DFS to find this chain. So we want to find a chain from like vertex U to vertex V. So we want DFS from L, and then our goal, then the vertex V is vertex R. It's like the index R. So like we want to find the chain. So you can code a DSU for this. So since we are doing DFS on tree, we also need to make sure you don't return to a parent. So let's add an extra parent variable there. Then if this thing returns true, that means we found the chain, so we can just return back true. In the other case, return false. So this should be able to give us the chain. Let's check that our chain is correct. Okay, we need to make some cases. So the first case is that the chain is initially empty. So we currently identified the chain as 1, 2, 4. Okay, then it's convenient for us to like have array for like what's the index of this thing on the chain. So for everything on the chain, Then now now we can do our DSU. Let's iterate through all things. So if at least one of them is not on the chain, so if X is not on the chain or ITX is not on the chain, then we need to merge them in our DSU. So we will union them. Then the answer is also equals will also be equals to X. Okay. Let's check if this works. For our, let's check if this at least that the first step works on our sample. See, something went wrong. Okay, I forgot to return. Oh wait, this should be cool. So this means it's not on the chain. Yeah. Then you see the second and fourth, they have been marked as like the answers too. All the rest are still 0. So let's focus on that case now. So now we just need to check. Now it's quite simple to check. Well, if they're in the same DSU component, right, that means that the rest of the edges will be fixed ready. So we can just assign everything here. Else we will need to do this. So let's write like, so this is like the current like process things on our chain. So CR equals 0, CR equals the size of the chain. That's all. So for convenience, let's also put the indexes on the chain. So yeah, we'll first union them, then we'll set the answer of CL. Okay, now that I changed like the type of chain, I need to like update everything. So let's just copy those. Check that works. Got something wrong on line 1, 2, 3. Oh yeah, this should be CR as well. Let me just check that the chain did nothing wrong. Okay, wait, yeah, there's an error in this code. Oh, okay. It's still not matching the sample output though. Let's see what happens. See what was wrong. Oh wait, yeah, I implicitly assumed that like, yeah, okay, wait. This is like a trick. This line is like a trick to like do the like multi-initialization in C++. It still didn't work. Just write out the values of R and R, see what is happening. Huh. Okay, we must. I always want to put the non-chain to a chain. This seems correct. Let's try submit this. So we want to put the non-chain into the chain. Well, runtime error on test 16. What can possibly be runtime error on test 16? Okay, let's just try small cases. Yep, seems to work fine. Well, honestly, yeah, I don't really want to feel like debugging this, so just like look at the, I mean if it's big I still have to debug it anyway, so let's just see what went wrong. I honestly have no idea what this means. Let me just see if I can like eyeball this. Okay. Will this work? This is like the way to be lazy about debugging. See, let's see the assert got triggered. Oh yeah, the assert got triggered, so something definitely went wrong. Oh yeah, I think I know what went wrong. It's like the way we call the DSU unions is that we always want to like merge with something on the chain. You know, instead of making the logic over here, right, why not we make the logic inside the DSU function itself? So I think that will simplify a lot of things. So if I is on a chain, then we move J becomes the son of I. Yeah. So I mean, for this problem, right, the main idea you want to do is that you just want to play around with cases where you think about like a single variable. Then this will like greatly simplify the problem. Got AC already, yeah. What contest is this from? 2 weeks ago. Okay. Yeah. So I don't think we have enough time to go through another problem, right? And this is like a very short problem because there's like the Google round that's gonna happen soon. So I guess this is a good time for us to stop.